All right, class. This is our last lecture, and a very important lecture. It's a sort of a separate topic. I could address this at any point in the course that I had, extra time or whatever, but it's important that we get this, even as the last lecture, the stress concentration factors, and I want to point something out. And you probably have suspected this the whole time that we have been talking about, normal stress or shear stress, and this applies to shear stress as much as it does to normal stress and everything else. When we have discontinuities in the cross section, how does that manifest itself? And so I'm going to say that, let's say that I had a hole that I had to cut in. I hope I've drawn that correctly. And I've got a uniaxial force P placed on this. Now, how is that going to change things? Because now we know that this is going to have a reduced cross section, right? I have a reduced cross section down here too. So we've got a reduced cross section at the hole. And I think the best way to sort of see this is, let me just draw that reduced cross section, because we've cut a hole out, right? So we've got a reduced cross section. So let me just use some numbers so that you can see what I'm doing here. Let's say that this is 10 centimeters and this is 1 centimeter thick, right? So if we look at the cross-sectional area of the tensile specimen, and we can put a force on there, we see that we've got 10 square centimeters. So I'll say that the cross-sectional area, 1, is going to be 10 square centimeters, right? Which would be 1 times 10 to the minus 3 square meters, but we'll talk about that later. Now, let's say that this hole right here was going to be a diameter of 6 centimeters. That would leave 2 centimeters up here, right? And 2 centimeters down here. So this distance is 2 centimeters. And the distance up here, of course, would also be 2 centimeters. Does everybody see what I'm doing, so that we can get that reduced cross section? So my reduced cross section is going to be 2 by 1 plus 2 by 1. So that's going to be 4 square centimeters, right? Does everybody see what we've got here? I'm just adding up those 2 different cross-sectional areas. So that's reduced. So you're probably thinking, okay, well, here's what it would be. If I've got this reduced cross-section and everything here, well, I can't use this cross-sectional area up here in here. And in fact, what I'm thinking is probably at this reduced cross-sectional area is where the thing is going to fail, right? I would think, well, okay, if I start pulling on it, right in here is where the thing's going to fail. But what is the force that I have to put on here to make it fail? Well, let's say that the material that's in here, that the maximum normal stress on that material is 300 megapascals, right? And we know that this is just going to equal the force that we put on it divided by the cross-sectional area. So if I was to use this cross-sectional area here, let's just use P, right? So P equals 300 megapascals times one area, right? So let's use the AX1 area first, right? So that means that the force in AX1, I'm just going to circle that so that I don't have to write it again, right? So I'm going to use that 10 square centimeters. And of course, like I said before, 10 square centimeters, I'd have to divide that by 10,000 to get square meters, wouldn't I? And of course, that's 100 centimeters to a meter squared gives me 10,000. So 10 divided by 10,000 is going to be 0.001 square meter, right? So that's what AX1 is. And then I'm going to multiply it by the 300 megapascals. I thought that I'd just do it, but I didn't want to lose anybody there. All right. So let's do that. So 0.001 times 300. Oh boy, I forgot to turn it on. 0.001 times 300. And that gives me 300,000 newtons, right? Megapascals, pascals times that squared, that would be squared, that'd be kilogram meters per second squared, so that would be newtons. So 300,000 newtons is what I would be able to pull on here if I just had that cross section. I didn't have the hole in there. But how about when I do have the hole in there, right? Because then it's not going to be 10, it's going to be 4 square centimeters. So now that would be P1 or PX1. Let's put that there. And then P X2, I'll call this, or X reduced, I don't know, I'll call it AX2. I don't want to write out reduced every time. So PX2 is going to be 0.00, but it's not 1 anymore, it's 0.04 square meters times 300 megapascals, right? So PX2 would be just a second. 0.0004 times 300 megapascals is 120,000. So you're going along and you're looking at this machine part that you're designing. You're going, okay, well, oh my God, no, we cut a hole in here to get that other part through, or whatever it was. So yeah, I can't use the cross sectional of this. So the maximum, I can't put the maximum 300 newtons on there. I guess because of the cross sectional area here, I'll have to reduce it down to 120,000 newtons. Right? That's what you're saying. So you're saying that's the maximum. That is not the maximum. The maximum, and I can tell you this because I'm an engineer and I know this just by by habit now, because I know stress concentration factors and I know how important they are. I know that the maximum force that you can place on there is going to be 40,000 newtons. And if you place that 120,000 newtons on there, that thing would crack wide open. Why do I say that? Because the stress at a concentration point is going to be 1 plus 2b over a, where if I have an ellipse like this, right? This distance is b, this distance is a. Just a second, I got someone knocking at the door. Oops, wait, gotta pause you. Sorry about that, and I am back. I just had to go. A neighbor came over and had to see me about something for a minute, but I'm back. We're looking at this, and this is why I'm saying now I want to point out it's not only internal that these, I haven't turned my mic off or anything, have I? No? Let's see. Yeah, okay, good. This is not just internal holes that we've cut out here. For instance, what if I had instead something that was filleted like this? Right, let me just draw this, you know, right? Isn't that the same as cutting a circle out? I've got to fill it up here, and then I've got to fill it down here, and now I'm working with a reduced cross-sectional area. I better draw it in 3 dimensions, or nobody's going to be able to see what I'm doing. Right. Right, so if I'm pulling on this and I've filleted this too, you're thinking to yourself, oh, okay, well, I just have to now, because I put a fillet in there and everything, I don't have to worry about it. Yes, you do. You still have to worry about satisfying this equation. And so anytime that you've got this discontinuity, even if you've got a perfect fillet there, even if you've got a perfect round hole there, because of course in a round hole, let's look at that one example. Circular hole, right? Wouldn't that be the minimum? Wouldn't that be? Oh, wait a second. Yeah, that is this times x2. I have x2. Sigma. Yeah, at x2. So the stress that we find at this point right here. Okay, so basically I'm saying that K, the stress concentration factor, is 1 plus 2B over A. And that's really how we write it anyway. Now, a circular hole, A equals B, right? So K is going to equal 1 plus 2A over A, if you want to do that, or B over B, or whatever you want to do. So K minimum, the minimum K you're going to have at a discontinuity is 3. Does everyone see that and understand it? I still have to use the reduced cross-sectional area, and then I still have to reduce it by 3 here, or I have to, figure out the stress will be that much higher. So to look at this, what I want to do is I want to take 3 examples now, or look at 3 different types. In fact, where could I draw it? Probably over here is better. So I'm going to have, just similar to that, I'm going to have a tensile specimen, right? I'll even draw it in 3 dimensions so as to make it look really nice. And now I'm going to put 3 things there. I'm going to put a circular hole. That's going to be, I didn't draw, right? But 6, let's call it 6. I should probably just erase that. And, let's see, 1, 2, 3, 4. So if that's 4, and I'm going to say that's 10, then each one is 2.5. Boy, I blew that one, didn't I? So oh boy. Well, I'm going to make it larger than that anyway. There we go. So now I'm going to say that diameter of that hole is going to be 6 centimeters, and that the full distance, boy, I can't get that in there anywhere, is going to be 10. Now, I'm going to do 2 other ones. I'm going to do one that's an ellipse this way, right? So we can use this circular hole as a pass-through, and I don't know how I'm going to draw that I think like that. That's pretty good. And that probably could go like that or something, right? And then I want to draw another one that's the other way. That's 6 centimeters long, but it's going this way, right? So this is going to be 6 centimeters. And this is going to be 6. Well, I've already drawn that. That's 6 centimeters too, right? And it's also going to be 1 centimeter going this way. All right, and so is this. This one's going to be 1 centimeter. I can't really draw it anywhere, but I think everybody can see. And I'm sure I haven't drawn it to scale, so that's also going to be 1 centimeter. And then the side, the full side here, is going to be 10 centimeters. All right. So what we want to do is we want to look and see what the actual stresses are going to be. Now, in this one, if you look at it, that, right, we've got a reduced cross section there and down here, and we've got the same reduced cross section up here. So these are both going to have the same A sub x2, but not this one, right? This one is going to have a much larger, right? Because we've put it now all of these, and this is 6 centimeters. All of these, by the way, are being used for pass-throughs so that we could put something like a wire or something through here. And so what I want to show you is which one of these 3 designs is best, right? You're designing a robot. You've got to have a pass-through for some wires just between some things. It's just, it's not going to chop any wires off or anything if it's too, all of these would be perfectly large enough to work. Which one should we design in there so that the robot then can maximize the uh, forces that it can use with that machine part that I've got there, right? And I think everybody can see how this is going to work out. Okay, let's do the 3 X2 areas. So what can I do? Oh, okay, I'll do it this way. So A sub x2 for the circle. We know what that is. That's going to be 4 square centimeters, just like it was the first time. And that would also be exactly the same as A sub x1, wait, or A sub x2 for the slot. I'll call that a slot, but not for the ellipse. I'm going to put the A sub x2 for the ellipse. We already know what A sub x1 is because I haven't changed these as all. This is still 10 centimeters by 1 centimeter, thick, right? So that's 1 centimeter thick. Not drawn to scale, that's my disclaimer. And then AX2 for the ellipse is going to be just 1 centimeter out of there. So it's still going to be 9 centimeters by 1 centimeter. So that's 9 square centimeters, right? Okay, so let's place our 40,000 Newton force on there and see what type of things we get out of it, right? What type of stresses for these 3 things. So the stress for the circle, right? We want to take A sub x2 for the circle, or 4 centimeters. And of course, we've already really done this because we got square, that's 6 centimeters. We've already done everything. And we know, but I'm going to actually write it out this way, right? So we've got the 40,000 newtons divided by the cross-sectional area, and we've got to use a sub x2, so it's going to be 400 times 10 to the minus 6 square meters, right? Or 0.4 times 10 to the minus 3, however you want to do that. And then we've got to multiply this by k, right? And we know for a circle that k is going to be 3. So why is that not seemingly coming out to 1/3, 120.4 times 300 megapascals, and then 3, so 120. Yeah, that'd be 120 divided by, let me just plug that in here and see if I actually have done this right. 120,000 divided by 400 to the minus 6. And that gives me 300 megapascals. That's right. So there you go. Right? So if we did it with the circle, and of course that's how we designed this, right, with the circle, the thing would be perfectly fine. But what if instead somebody who wasn't really skilled as well as we are cut the slot in this way rather than making it a circle? He thought, what the heck? Why make it a circle? I'll just, make a slot in there. The wires can go through it just as easily. I don't see why I have to make it a circle, because he doesn't understand. He's an electrical engineer, and he doesn't understand the mechanical engineer's design of it. And so he decides, well, I don't need all of that room there, and it's taken up way too much room. I'll just cut this little thing out of here. But what he doesn't realize is that by cutting the slot transverse to the way that the forces are being applied, that he's actually going to cause that part to fail and everyone in that airplane to die. Right? So let's go figure that out. So for the slot, how much stress is actually going to be on there? Well, we have the 40,000 newtons, right? Just like we did before, over 400 times 10 to the minus 6. I don't know why I just didn't write 0.0004 square meters, right? But now, what is our K value? It's 6 to 1, isn't it? Isn't that 6 divided by 1? 6 high divided by 1 wide. You see what that electrical engineer has accidentally done? He's actually put a stress concentration factor of 6 plus 1, right? That's, oh no, actually 12 plus 1. So he has increased the stress concentration factor from 3. That's why the mechanical engineer actually put the circle in there in the first place. And instead, by cutting the slot in there, he has taken it from, this is 6, 2 times 6 is 12, plus 1, 13. So what is the stress that's going to be occurring on the top and the bottom of this slot because somebody changed it afterwards that didn't have the expertise to actually make that change? I'll tell you. 400 minus 6, that is 1.3 gigapascals. Yeah, long time before it ever reached 1.3 gigapascals, that failed. Right? That mechanical part failed, and then there was no fuel to any of the engines over the Pacific Ocean, and what do you know, it didn't work out well. Now, let's go and see what instead. Let's say that the electrical engineer was lucky, and he just, he didn't know anything. He doesn't had no idea of stress concentration factors because he had never had this class with me in Wentworth, right? But he got lucky, and instead he cut the slot along the same direction. He cut the slot along the same direction as this. Will that mean that the stress is even less and less and less? Of course it does. Let's look at that. So for the ellipse, Notice I gave it a capital letter. All right. Now it's going to be 40,000 newtons again. That's a comma. But now it's not 400 anymore, is it? It's 900 times 10 to the minus 6 square meters, isn't it? And what's our stress concentration factor now? You know, B over A, isn't this 1 over 6? 1 over 6. That's 1/6. 1/6 times 2 is 1/3. So my K factor now is 1.333, isn't it? Oh my God. If instead that electrical engineer had cut it this way instead of that way because he had known that this is going to diminish the stress concentration and this is going to accentuate the stress concentration, if he did that, he'd get promoted, wouldn't he? He would get promoted. I don't know if that's actually the case. It was in my case. No, I'm kidding. But, you know, so let's actually let's just, so a comparison. So 40,000 times 1.3 divided by a larger cross-sectional area, 900 times 10 to the minus 6, gives us 57.78 megapascals. Now, look at what we've done. Just by turning it this way, getting rid of the circle, don't do it this way, do it this way, we have cut down from 300 megapascals to 57.78 megapascals, right? So, could we now increase the force? How much could we increase that force up to before this gets to 300? Right? So what's our maximum force now, because we're such geniuses that we actually switch this the other way around? Well, let's say it would be 300 megapascals. Isn't that what we're shooting for? Divided by 1.33 times 900 times 10 to the minus 6. And instead of my maximum being 40,000 because of the hole that was put there by the mechanical engineer, and then you say, hey, that hole, we can change that hole into this ellipse that's you know, oriented parallel to the transverse, to the uniaxial loading, right? And we can actually increase. So what's our new force? 300 megapascals times 900 micro divided by 1.3333 equals 202,505.1 newtons. You are promoted, right? See what the stress concentrations mean, what you've got to do, and remember, you got to take it into account here too. Not only that, what if I had a torsion rod that had a discontinuity here, right? Isn't that discontinuity like infinity, right? Let's say that I'm torquing on this torsion rod, and you know, I don't even know how I draw that. Something like this. Yeah, and so I'm twisting on this torsion rod, and I've got a discontinuity here, right? So that discontinuity at the top and bottom, that's where it's going to break, because if I look at this in cross section, I see that I have something like this. So what you want to do is you immediately want to fillet these out. And how do you want to fill them? Right? On a semicircle, don't you? To minimize that thing. So you'll go like that, right? That's how you want everything to be smooth. No jagged edges on any of the things that you're doing, or that just adds an infinite stress concentration factor. All right, well, thank you very much for the whole course and everything, and make sure you do the 3 tests, and oh, you'll be doing the 3 tests and the homeworks and the, writing up the labs and all of that too. But this is going to take care of the lectures anyway. All right. See you in class.